So welcome to this lecture, the last lecture that we have together. So the plan for this lecture is the following. So I want to discuss very briefly about finite memory strategy, but with specific aspect to complex material model, to nonlinear material model. After we'll continue with a little bit of theory about material nonlinearity. We'll continue discussing with the elastoplastic case, but I want to present you advanced yield surface. We will continue to discuss about viscoelasticity, and we will also extend the plasticity theory to the viscoplasticity. And I will also discuss about damage. So just a few aspects that you have to consider when you use a nonlinear material model, because it's a very complex material, so you cannot use directly if it's a new material with a new parameter, so you have to be sure that what you are modeling is correct. So for this, you need to make some verification. So first, like theoretical verification. What mean? You can take a very simple case. For instance, we have seen last week that you can model like an elastoplastic material. So you need to have such a material parameter like yield stress and hardening. So you can, for instance, you model like a tensile test. You put like a yield stress like 1 megapascal initial yield stress, and after you reproduce this very simple test on Abaqus or whatever finite element software, and you just verify that the yield stress that you input is what you get as output. So it's like a theoretical verification. That means like a very simple case that you know what is the answer of this test, and you make it on your finite element software. So this is the first verification. That means so you have understood exactly how the model is working, so you know exactly what you need as a material input. So this is the first step. And the second step is the experimental validation. So if it's a new material model, so if it's a new finite element simulation that you want to perform, so you are not sure about which material parameter, since it's very complex, so you need like to validate this experimentally. So to be sure that the response that you get from your simulation is correct, is able to model the reality. So in experimental validation, there is also two levels. So the first level is back predict test. What's mean? So let's say so you want to model this kind of material. So you have like a nanoplastic material will damage. So the stress. So this is a stress strain curve. So it's going up. There is like a peak stress, and after this point, so somewhere here we can say that there is plasticity, and after this like plasticity combined with damage. So let's say you find a material model in Abaqus to model this behavior. So you have to give like the hardening, the peak stress, and after the damage evolution. So you use this test to identify your material parameter. So that means you are performing this test. So here is like a compression test. So from this test, you can deduce like the peak stress, and you can deduce like the damage evolution. So you identify your material parameter from this test, and after, so you reproduce this test in Abaqus. So you verify that what you put as input is getting the good output. So that means you verify that the peak stress that you put is great here, and the evolution is okay. So this is the first level of validation. So on this, you can say, okay, I have the good material model to reproduce this test and the behavior of the material of this test. But you are not sure that you can make a prediction on another test. So if you want to validate your model, so you have to validate on a structural test. What is a structural test? It is a test which have the response which depend of the structure of the geometry of the material. What means? So here is like a test. I already discussed about this test very quickly. It's like an indirect tensile test. So you apply compression load on a cylindrical specimen. So it's compression on this direction, then on the transverse direction, due to the geometry of the specimen, you have a tension in the middle, so tensile stress. So if you make this test with a different size of specimen, you will get a different behavior. So this is like a structural test. That means a response depends of the geometry. It's not the case on material test. Material test is able to identify intrinsic parameter of the material, like a Young modulus, like a yield stress, etc. So here there is like a certain geometry of the specimen. So it's like a cylinder with a certain diameter. So if you change the geometry, if you take like a wider cylinder, so you will get the same material parameter, same peak stress and same damage evolution. So of course, if we discuss about stress strain, so that's why it's like material test. So it's a test able to identify intrinsic material parameter. So the aim here, so is like you make an experiment. You don't use this experiment to identify material parameter. This, in the case of structural test, this test is only used to validate your model. So this is like a three-step validation. So the first one is like very small theoretical verification. You know what is the response of like a tensile test on the one element, the theoretical response. So you make this on Abaqus and you verify that everything is working well. Second step is to predict the material test that you have used to identify your material parameter. And the third, the highest level of validation, is to reproduce a test that you have not used to identify material parameter, and especially a structural test. So a structural test which have a complex geometry, which have a good chance to have a good validation for your model. So when you have performed the three-step of validation, so you can now you can postulate that your model is able to make some prediction, because the aim of the finite element simulation is to make some prediction. So what means you want to see what will be the structural behavior of like an engineering structure after a certain time. So you want to make some prediction. So to be able to make some prediction, you have to take some verification in order to be sure that your model is able to predict. There's just a few words about the difference between material test and structural test. This is an example of material test. So as I told you before, is the same example is like uniaxial compression test. So this is a material test in theory. So that means you can deduce some, let's say you want to deduce this parameter, so the peak stress. So that means the stress when you have like the maximum stress on your stress strain curve. So that means starting from this stress, your damage initiate and your structure start to fade. So let's say you don't really know which kind of geometry you want to use. But so let's say you are performing your test on 3 different geometry. So you have 3 different diameter and 3 different height for this cylinder. So this is a response of the test. So this was performed on asphalt concrete specimen. So this is like a peak stress. So the material parameter here that you want to characterize in function of the ratio between the height and the diameter of this specimen. So we have performed two experiments. So the first one without friction reduction, and the second one with friction reduction. Why I discuss about friction reduction? Because if you don't have good friction between the cylinder and the clamping system here, so the plate, so you can have like something that we call buckling effect. The shape can have like this is like a barrier. So you have like you deform the specimen non-uniformly along the longitudinal direction. So if you look this with a bad friction between the plate and the cylinder, so you can see like the peak stress vary depending on the geometry. So you can have like 11 megapascal for the peak stress with this ratio. Wait, sorry. And here for this ratio, so 2.5, you have like 5 megapascal. So that means that the geometry of the specimen has an influence on the response. So this is not a good material test, because you cannot deduce like an intrinsic material parameter, because when you are changing the geometry of the specimen, you are also changing this value. So what you will put in your finite element simulation, will you put 11 or will you put 5 megapascal for this peak stress? This is not correct, because you are performing a simulation. So let's say, so this is like a asphalt concrete specimen. So you characterize this peak stress, and after you want to model like an entire pavement. So it's not like a cylinder anymore. There is no this ratio of geometry. So you cannot use this one or this one. You have to use like an intrinsic material parameter. So now if you are looking the red result, so with an appropriate friction reduction, so on this, the specimen will deform uniformly. So it will be like a cylinder along all the test. So you have like a uniform stress state inside this cylinder. And on this, you can see that you obtain always around 5 megapascal for this peak stress. So on this, that means you got like an intrinsic material parameter of this asphalt, for instance, in this case. So that means it's a material parameter that you can use in your material model for your finite element simulation. This material parameter doesn't depend on the geometry. So this is like an example of what you have to consider as input in your finite element simulation. If you consider like this kind of test with this response depending on geometry, this is not correct to set up in your finite element simulation. You need to use like intrinsic material parameter. So when you are doing like a finite element simulation, you have to be sure that what you are doing, especially once you want to deal with material nonlinearity, since they are quite complex materials. So you have to be sure the input of your simulation. So this was an example of material test. So with a red result for the peak stress. For instance, if we discuss about asphalt or pavement engineering, this simulation I can put again. This simulation is a good example of structural test. So it's like a wheel passing on the pavement. So this test is like a wheel tracking test. So you can see here. So it's like a wheel passing on a structure, so on a pavement. and this wheel can pass with a very high number of cycles. So it's like an accelerated small road in order to understand what happened in a long time. So with a high number of cycles. So this is totally dependent of the geometry. If you have like a road which is which have a different geometry, which is wider or which is which have like different boundary conditions, so it can be like confining. Right? It can be, there is different possibility of performing this test. So this is totally depending on geometry. So you cannot deduce material parameter. You cannot deduce intrinsic material parameter for this. So this is only used for validation. Okay, so I want to close the parenthesis about the different material test and structural test. I wanted to present this because I want you to be aware of what you have to perform experimentally if you want to make finite element simulation with nonlinear materials that you don't know, that you are not used to work with. Of course, if you are designing a bridge with a steel which is very well known, where you know all the material parameters, so you don't have to go for the step experimental characterization and experimental validation. But this is not always the case. So if you want to use a new material, or if you want to use also materials that you know, but a new material model, so you have to be aware of how to make your finite simulation great. I mean, how to be sure that the predictions that you are that you will have, that you will get as output of this finite simulation are correct. So here, if you look under like this wheel passing on the road, so you can see that there is a like different stress level. So just here under the wheel, so you have like a biaxial compression. And here you can have like a shear around, and here, just here, if you see that this the pavement is going up, that means you also have tension here. So around here, so you can have like tension on this direction and compression on this direction. So that means you have a very complex stress state. So let's discuss a little bit about stress state. So we have seen last week that that there is like a certain point when the plasticity starts. And this point, so if we take, for instance, here the uniaxial case of compression, so there is this point here according the second direction that I will that I put here in red. So that means no stress on the stress one direction, only in the second direction because it's a uniaxial compression load. Now, let's say you have like compression according the second direction and a little bit of tension according the first direction. What mean? That mean you have now this point here, so your yield stress here, which is around here. It's like combination of sigma 2 and sigma 1. So it's no longer on this axis because sigma 1 is different to 0. So you have here your yield stress. Now let's say you continue to have like a compression here according the second direction, and you have also tension here, but with a higher tension here. So here is your peak stress now. So that means if you put this on this graph, so you have this yield stress here. So if you do this for a lot of stress states, so here I took the case of compression tension, but you can have also like, if you are here both positive, you can have like a biaxial tension, you can have like here biaxial compression, is both are negative. And if you do this for a lot of different stress states, so you can start drawing your yield surface. So this is like a complex yield surface, which is like, for instance, for a lot of material, for instance, asphalt concrete. This is also the case of like material like soil. So you will certainly see this with SADC during the next lecture. So as you can see here, you have different yield stress depending of the stress state. So here, at the point where sigma 2 is equally to sigma 1, so you have like the case of biaxial tension, when you have a tension, the same tension according both direction. So this is a kind of advanced yield surface. And if you remember, last week we discussed about the von Mises yield surface. So I presented you the most easiest elastoplastic model using the easiest yield surface. It was a von Mises yield surface. Why this surface was very easy? Because it was the same yield stress is for all the different stress states. So if you are in tension, uniaxial tension according to second direction, so you are at this point. And if you are like uniaxial compression, so when you have a negative tension according to second direction, you had the same value. It was just a sign. It was a difference, but the value of this, if here if it were 1 megapascal, it's also 1 megapascal here. Is the same, and there is also no influence on the direction. So that means if you load your material according to the first direction here, it's the same as here. So these values, they are all equal. So that's why this model is very easy to use. But this model is not very realistic for many material, like asphalt concrete or soil, as I mentioned, polymer. So there is many material which cannot be modeled with the von Mises yield surface, because this surface is not able to model the complex stress state. Or I mean, this model is able to model complex stress state, but the response will not be correct. So let's plot the von Mises stress surface on another graph. So this was a von Mises criterion that I presented you last week. So this was this von Mises equivalent stress that I presented you last week. And this von Mises equivalent stress is plotted in function of the hydrostatic pressure, P. So if you remember the hydrostatic pressure, it was a trace of the stress tensor. So what mean the sum of all the term on the diagonal of the stress tensor. So what mean if you are in pure tension, you have something which is positive. So that's why on the positive side of this axis, I wrote tension. That means here it's like tension. So pure tension is somewhere here. There is also biaxial tension. Even triaxial tension is also like a stress state somewhere on this axis. On the other way, when this hydrostatic pressure is negative, so you are like in compression state, because again, this P is like the trace of this diagonal on your stress tensor. So if you have something negative, so that means you are in pure compression. If you are in compression, it can be pure compression, can be biaxial compression or triaxial compression, etc. So that means negative compression and positive tension. So if you remember here, von Mises shear surface, if it's negative or positive, it's the same value. So what mean this F, which is your yield surface, which is your limit, which must always be equal to 0 when you are in a plastic state. So this is constant for all the different stress states. So that means you don't have any difference in compression and tension. And as we have seen here, this is not the case for a lot of material. So here, for instance, when you are in compression, this value is very higher in comparison to this value. So now I want to present you like a new criterion to determine the yield surface, which is a Drucker-Parger criterion. So this is like we can say it's like a modified version of this criterion. So we have used like a new material parameter alpha in order to get a yield surface which depends of the hydrostatic pressure. So if you look here into the mathematics, if you put like alpha equal to 0, that means the hydrostatic pressure sensitivity disappears, and you get the same criterion as the von Mises. So now you have like a yield surface here, which depend on the hydrostatic pressure. So by doing this, so this is like how to characterize a material parameter alpha. So by doing this, so you can see that you can have like a higher yield stress in compression than in tension, as we have seen here. So you have higher yield stress in compression than in tension. So this is the Drucker-Parger criterion. Again, if I make the link with the experiment, if I needed only one test to characterize the yield stress for using the von Mises yield surface, now for the Drucker-Parger, since it's not the same yield stress in compression and tension, I need at least 2 experiments to characterize. So of course the limit, but the limit for different stress states. So the limit may be in pure tension and the limit may be in pure compression. And since it's linear between, so two experiments are needed to identify this yield surface. So as I present you, this new yield surface so is depending on the hydrostatic pressure P. So we classify this kind of criterion pressure sensitive yield surface. You will discuss a lot about this pressure sensitivity with SADC because it's the same idea that we have with soil material. So SADC will discuss about the Morcoulon material model, which is very close to the Drucker-Parger, in fact. Okay, so as I was presenting, so this Drucker-Parger criterion so is now pressure sensitive yield surface, so it's able to take into account the difference between compression and tension, but also by doing this, it can also identify a model like a complex stress state. So it can be like pure compression, it can be like a compression with a little bit of tension, etc. So, or it can be like pure tension. So this is the idea of like using an advanced yield surface is to be able to model a more complex stress state. Yeah, so this is like this kind of criterion that you must use if you want to model multi-axial loading. So like when you load on not only on one direction, but when you have a complex loading. So there is many advanced yield surface. So this was the first case. So in 3D, it was like this cylinder, it was a von Mises. So this is like the easiest as possible. So no difference between tension and compression. If you look this Drucker-Prager, as I presented you here. So here, if you plot this in 3D, is like a cone here, which has like the hydrostatic pressure as axis. So here is like the linear Drucker-Prager in 3D. So the axis of this cone is the hydrostatic pressure. So along this hydrostatic pressure, so you can model the difference between tension and compression. So when here, when the diameter is smaller, is like under tension, and when the diameter is higher, is under compression. You can have also like other kind of surface like Gersson. So you have like a variation along the hydrostatic pressure, but you also have like a saturation. And so this is a case of smooth yield surface like von Mises linear Drucker-Prager, but there is also different yield surface which are smooth like Tresca and Moore-Coulomb. So if you see Moore-Coulomb, it's very similar to linear Drucker-Prager. So I cannot say it's a cone, but there is also like a difference between tension and compression, and it's also around the hydrostatic pressure axis. But is like a non-smooth yield surface. And there is also very complex yield surface, which can take into account the different tension compression, which are like a saturation. So there is many different yield surface. And of course, you cannot say, okay, I will always use linear Drucker-Prager because it's working better. It's of course depend of your material. There is some material which have no pressure sensitivity, like aluminum material. So in aluminum material, you will not use a linear Drucker-Prager because you don't have different. I mean, plasticity, there is no difference in terms of tension or compression. So of course, your yield surface should be in accordance with the materials that you are modeling. So you have to be aware of all this aspect, and you have to know what is the purpose of an advanced yield surface, why I should use this yield surface or not. Again, is not you cannot use a very advanced yield surface for all the material. You cannot say I will use this because it will work for very complex material, so it will work on a simple material. It's not working like that. All the different material have different yield surface, so you have to choose one yield surface which is good for this kind of material. Yes, this is like an example of the material response of an asphalt concrete. So as you can see here, so the red curve is the response. So is a behavior law in a compression, and this yellow is a behavior law in tension. So as you can see, this is a very higher in compression than in tension. So that means if you only perform one test and you use the von Mises yield surface, so if you are performing this test in compression and you determine, let's say, this peak stress in compression, so after you will use this material parameter, the peak stress, in your finite element simulation, if you try to model the compression behavior, so you will able to model this curve. It will be totally fine in compression. But what happens if you try to model this tension? If you have only one parameter, so you can only use the von Mises yield surface, so that means in tension you will have the same curve. So you will overestimate a lot the material behavior. The same in tension. So if you identify the peak stress with a tensile test, so you will get this point. So if you use like a simple yield surface with only one parameter, so you will afterward you will simulate this in Abaqus. If you model a tensile test, so you will be able to reproduce this curve. But now if you try to model the compression, you will also have the same curve because von Mises yield surface is not able to make this difference. So you will underestimate a lot the behavior. So that's why it's very important to be aware of which yield surface and also which test that you have to perform to make the good simulation. So here, what you have to do is to make a test in compression and in tension to determine like the peak stress in both, so in compression tension, and use the Drucker-Berger yield surface, which is able to take into account the difference in compression and tension. So when afterward, when you model in compression, so you will get this curve, and due to the pressure sensitive yield surface, when you will model tension, so you will also be able to model this part. So you will have a very better response of your simulation by using an appropriate yield surface. Yes, so here it's an example of advanced yield surface. So you can see here, so here I model also the viscoplastic effect. So that means this yield surface has different value depending of the strain rate. So we will discuss a little bit about this after. I want to show you that here, like generally, so this is like a Drucker-Berger, but after a while there is like a saturation effect. So it's like a viscous capped yield surface. So it's like you have like a saturation effect after a while. So you can have also like viscoplasticity. You can also have like temperature dependency on the yield surface. So like the topic of selecting a good yield surface for complex material is kind of very, very complex. So for characterizing, we discussed, so you can use like a ID test to identify tensile test, compression test. And if you, so here I present you like these two cases. So like compression and tension. So with a tensile test and compression test is enough. But if you want to model like this saturation effect, so you also need to perform like triaxial test with different hydrostatic pressure. So you need to increase here the stress level here. So you can use this kind of device here, where you can perform a compression test, and you can apply also like external pressure. So you are confining this, so you are increasing a lot the pressure, so the stress state of your specimen, so you can capture the point here. So what I mean, if you want to use this kind of very advanced and complex yield surface, you also need to have the experiment in accordance. So you always have to compromise what you can do and what you can perform in terms of experiments when you want to simulate. Because if you use this very complex yield surface, but you don't have the good material parameter, so you can have the saturation very early, which will not be good in terms of modeling, or you can also have a saturation which occur late. So you need to, it's not good to use a complex material model if you don't have the appropriate experiments. So you always need to have this in mind when you are performing finite element simulation with a nonlinear material. I want to continue with the theory of advanced yield surface, but I think we can take a break now, so 15 minutes. So I will stay here if you have any question. Okay. Yes. So with the Van Mises criterion, if you remember, we also determined what was the flow rule. So what was the evolution of the plasticity once you get to this yield. So what happened after? Because this yield is was only to determine when the plasticity starts, but after when the plasticity starts, so you have like an evolution of this plasticity. So there is like how the viscoplastic strain evolves. So that's why here it was like this epsilon dot p, evolution of viscoplastic strain. This was determined by that we call the normality rule that I presented you last week. So it was like the plastic multiplicator multiplied by the derivative of this year surface by the stress. And this was giving you something like that. So now if you calculate the volumetric strain according to the von Mises criterion, what is the volumetric strain? Is like the trace of the plastic strain tensor. So volumetric strain, the total strain, so is a trace of the strain tensor. And what happens if you always if you only do this on the plastic strain tensor, so if you make the trace of the plastic strain tensor, epsilon p, you get something which is equal to 0. If you want, you can try this. You can take whatever stress state as possible. You can take a tension, compression, biaxial tension, etc. By definition, by the mathematics, the trace of what you get will always be equal to 0. Why? Because this is depending of the deviatoric stress tensor, and the deviatoric stress tensor is like the stress by deformations which have no change in volume. So deviatoric is a change in shape, but not change in volume. So the volumetric strain represents the change in the deformation due to change in volume. So basically, your material can increase volume or decrease volume depending on the if you are in tension and compression. So what's mean trace of plastic strain which is equal to 0? That means the plasticity. So the contribution of the plasticity in the change of volume is equal to 0. There is no volume change due to the plasticity. So you can deform your material up to fracture. The plasticity will not make an increase of volume. So of course you have a small increase or decrease of volume, but due to the due to the elasticity, due to the Poisson effect, but not due to the plasticity. So this is due to the mathematics of the von Mises criterion, because the evolution of the plastic stress is only depending of the deviatoric tensor, only depending on the stress coming from change in shape, not in volume. Now, if you take the Drucker-Parker criterion, and if you use so the normality rule to deduce what happened after, so what happened when the plasticity start, so to calculate the evolution of the plastic strain, so epsilon dot p, so you take the same formula, so you take the derivative of your yield surface by the stress, and you get this deformation. As you can see here, there is something which depends on the deviatoric stress, but not only. There is also something here. So what mean? Now, if you take the trace of your plastic strain, you will get something which is not equal to 0. What means the volumetric strain due to the plasticity is not equal to 0. That means you will have a change in volume due to the plastic phenomenon. So to summarize, there is no change in volume due to plasticity with von Mises criterion, and there is a volume change due to plasticity in the Drucker-Parger criterion. As you can imagine, the Drucker-Parger criterion is better to describe such kind of material like asphalt concrete or soil or polymer. It's not here. So as you can see here, this is a volumetric strain. As you can see here, even so here we cannot see where is elasticity and the plasticity, but is somewhere around here. Here is like negative is when it's elastic, and here it's when it's plastic. But that you can see here is there is like an increase of volumetric strain when you increase the strain. So certainly when you increase the plasticity. So if you use the Van Mises yield criterion, so you will have not this kind of evolution for the volumetric strain. So what means you will not able to model the volume change, the real volume change of your material by using the Van Mises criterion, because this material change volume with the plasticity, and with the Van Mises yield criterion you will not able to model the volume change due to the plasticity. So so now I describe you what is the evolution of the Van Mises and the Drucker-Parger. I mean all the material which have a pressure sensitivity yield surface. That means it can be like asphalt concrete, it can be soil material, it can be polymer material. There is many material. So, and all this material which have a pressure sensitivity have also an increase of volume due to the plasticity. So to be able to model this increase of volume, so you need to use this criterion. So here it's what is the evolution of using the Drucker-Parger model. And when you, so this way of calculating the evolution of the plastic strain by using the yield surface, which is called like normality rule. It's called associative flow rule. It's the rule that I present you up to until now. And we have seen that for the Drucker-Parger model, it gives you like a volumetric strain which is not equal to 0. So you will be able to model this volumetric strain due to the plasticity. But there is also another rule that we call non-associative flow rule. I can continue. So this is called non-associative flow rule. This is, you define two potential or two surface. One surface as usual F to determine the yield. So when the plasticity will start. So it's the same as on this case. But now, if you want to model how the plasticity will evolve when the plasticity starts, so we will use a new potential, which of course has a it's very similar to the first one, but the material parameter can change. So now I deduce my plastic evolution by taking the derivative of not this yield surface, but this second potential here. So now my flow rule is deduced from the derivative of J by the stress. So I get something which is very similar to this expression, but it's only like the material parameter here which change. Why we should do this? To get a better description of the volumetric strain. So we have already discussed about that, like this kind of yield surface, which take into account the hydrostatic pressure. When you take the derivative, there is something extra, is not only deviatoric. So that means you will be able to model the volumetric change due to the plasticity. But to have a better description, to have a more accurate modelization of this volume change to plasticity. So you can use a second potential, which have its own material parameter. Let me show you this example. Again, this volumetric strain of asphalt concrete. So maybe you, let's say you perform one test in tension, one test in compression. So you get sigma E. So like the yield stress in tension and yield stress in compression. So you can also deduce the parameter alpha. So you got the right parameter for the yield surface. So with this F, so you are able to model accurately when the plasticity will start. So you will be, so you have a good description of the starting of the plasticity. But what happened after? So if you take the derivative of this and you model the volumetric strain, so you model how the plasticity evolve. So maybe you can get this description for the associative. So you can have a volumetric strain which is not equal to 0, so which is already good, but maybe you can have something which is even better by using other material parameter that's something different that you have used for the yield surface. So that's been, you can change the material parameter when you want to describe what happened after. Sometime, if you are lucky, so you can have only 1 yield surface and you can perform like your finite element simulation and calculate the strain and look what is the volume change. And if with only one surface, you are able to model when the plasticity start and how the plasticity evolve, and if the volume change is accurate. So this is great. You don't need to have an additional surface, additional potential. But if you are in this case, if you model the volumetric strain and you figure out that you are not modeling accurately the volumetric strain, so you can like add a new potential, and so your material, so your plastic strain will be deduced from a new material parameter beta. So on this, you will not change the first yield surface. So you will not change when the plasticity starts. So on this, you will continue to be accurate, but you will get a better description on the volumetric strain. So this is the case of non-associative. So to summarize, non-associative flow rule is like when you have two different potential, two different surface, one for the yield and one for the evolution. And this is used to have a better description of what happened after one, or to have a better description of how the plasticity evolves. This is an important concept in modeling, in material modeling of pressure dependent yield surface. Yes, so that's it for the advanced yield surface. Now I want to discuss a little bit about viscoplasticity. How can we extend the theory of elastoplasticity that we went through last week into the viscoplastic case? So we discussed last week about this elastoplastic model, the simple elastoplastic model. So if you remember, so this was like a stress strain curve. So that was like the first part elastic. You have one initial yield, which was a sigma y0 here. And after you have like this yield, which is growing due to your hardening here, which depend of the plastic strain. So this was the elastoplastic case with linear isotropic hardening. sorry, this sigma v should not be here. This sigma v is here. This is like the case of viscoplasticity. So on here, we add a new term, sigma v, which is viscous stress. So that's why it should not be here. Viscous stress, which depend now of the plastic strain rate. So this is P. If you remember, it was the equivalent plastic strain. So this is the equivalent plastic strain rate. So now you have a term which depends on this strain rate. So you have like an additional contribution here that we call viscous stress. And of course, if you increase the plastic strain rate, so equivalent plastic strain rate, so it will increase this yield surface. So on this, you have like a surface which of course depend of the plasticity. So it can increase. So this is due to the hardening, and it also depend of the strain rate. So if you have higher strain rate, so you have a higher yield surface. Which means if you are loading your material faster, so you have higher limit, higher yield stress. So it is very easy to extend an elastoplastic theory to the viscoplastic case. Yes, so on this case is not F, is like FD, like dynamic yield surface. So because it's a yield surface which depends of the strain rate, so it's not static anymore, just a name. And this sigma V, as I told you, is called viscous stress. It's sometimes also called overstress. So it's like something that you have over the static yield surface. So if you take only this part, is a static yield surface. So let's say when you have strain rate which is equal to 0, which is not true in reality. You cannot have strain rate which is equal to 0. But if you have something which is very slow, so you can have like this static, and now you have a stress over the static yield surface. That's why it's called overstress, and this depends on the equivalent plastic strain. So that's why it's called viscous stress. So this is very easy. There is different. So what you can put as like a viscous stress. So there is different formulation for the viscous stress. The first one, for instance, something which is very easy. So you have like the sigma V, so the viscous stress. There is two material parameters, so K multiplied by the strain rate and an exponent. So that means you add this to this yield surface. So you have like a yield surface which depends of the strain rate, and you need to characterize two additional material parameters, K and M. So if you do this, you can write like the equivalent plastic strain on this form. There is other model which is quite common, is Persina model. So on this is all the yield surface, all the hardening which is scaled by this material parameter with this viscoplastic contribution. So you have two additional material parameter, and if you take the Persina formulation, so you can write the equivalent viscoplastic strain as this form. So as you can imagine, again, if you want to use a viscoplastic material, which is a case of like asphalt concrete or polymer material, you must perform additional experiments because you need to characterize new material parameter. So if you want to characterize, so you want to input material parameter in Abaqus for this yield surface. So that means you need as usual, so the initial yield stress, so the hardening, so the evolution. So you can do like a tensile test, but you need to do this at different strain rate. Sorry. Why? Because you need to determine the sensitivity of the strain rate. So if you are performing only with one strain rate, that means you will not able to evaluate the sensitivity. So you need additional tests to determine the material parameter for the viscoplasticity. But otherwise, this viscoplasticity is working exactly as the same as plasticity. So this is very easy. So the flow rules are the same. So how the plasticity evolve is similar. Is only the yield which has an influence of the viscoplasticity. I don't know exactly. Yeah, it should be positive. Yeah, it should be positive in the denominator. I think I will not continue to answer during this lecture because it will be difficult for me to continue. But yeah, to answer to the question, yeah, it's positive if you take this and if you put the denominator, of course. If you have some question, it's better to take it during the break. Yes. So let's continue with this. Yes. So this is for the viscoplasticity. But as I was explaining, this is very similar to the plasticity. So the rules are calculated according to the same formula that I presented you before. This is only to determine what is the yield, which now depends on the strain rate. So we went through the advanced plastic and viscoplastic model. Now I want to also discuss about what happened before this. So the viscoplastic is when you have the yield, and what happened after this yield. But if you have like a material which is depending on the strain rate, there is a good chance that this material is also depending before the yield. So when the material is still elastic, so if it's dependent on the strain rate, so when the material is viscoelastic. So I present you last week the viscoelasticity. So we finish this lecture with this general Maxwell model. So I presented you. So I've shown you that the stress can be calculated according to this formula, where sigma infinity is the stress in this spring, the long-term spring, and the sigma I in the stress is all the different springs. So this is able to model the the viscous effect on the viscoelastic part for a lot of different characteristic time. And this was the relation between the stress and the strain. So this, it was like a uniaxial test, like a uniaxial loading, where the stress and the strains are characterized with a rheological element. Yes, we have seen that this was like Pronisary in 1D, and it can also be written as like a Pronisary in 3D, where E infinity and EI are not scalar, but are tensor. So this was like this stiffness tensor, so the tangent matrix that we discussed last week, that you use to calculate your the element matrix, and you use to assemble in your global stiffness matrix that you need to solve your finite element solution. So I want now to discuss a little bit how to characterize the different material parameter here, because you will use this during the exercise. So it's good for you to understand where all the different material parameter come from. So if you remember, last week I discussed about what was the relaxation test. So when you apply a load, when you apply a displacement, and you maintain this displacement constant over time, so you have like a relaxation of the stress in your structure. So if you perform, so this is like an example on a polymer material. So if you perform a relaxation test at different temperature, so you can have this result. So here you have the same base of time, and you have like a relaxation test for many temperature. So as you can see, for many material which have like temperature dependency, when the temperature is higher, your material is softer, so you have like lower your modulus, and when the temperature is lower, so your material is stiffer. So what mean you perform relaxation test on many different temperature, and you obtain many curves. So what you can do with this, because in Abaqus you will not have like you will not have one curve for one temperature. So you want a one complete curve. You want one unique curve. And also what happened when the time is lower to this, and when the time is higher to this. So for doing this, so the aim is to compute something that we call a master curve. And for this, we will use a time temperature superposition principle. So what's this? The aim is to, at one temperature, so let's plot this. So here I plot this master curve for 90 degree. So this is a complete curve at 90 degree. And for plotting this curve, I only realize like horizontal shifting of the different curve. So if you look here, the curve at lower temperature, there was shift on the left side. So this curve is the same. This part of curve is the same of this part of curve. This part of curve is the same of this part of curve, this and this. So what means this had been shifted on the left side, this on the left side, this on the left side. And the curve with the temperature higher to the reference has been shifted on the right side. So this curve on the right side, this on the right. So if you look, this part of the curve is the same as this. So there is like some empirical formula to do this. And of course, this depends on the temperature sensitivity. Or you can even do this manually, because you know that there will not have a discontinuity in your material behavior. The curve cannot going up and down. I mean, there is always is going always down if you consider like a regression modulus. So you can, if you have sufficiently, if you have like an amount of experiment which is sufficient, so you can plot this curve without a discontinuity, and so you can have an idea of what is your master curve. So why plotting master curve? Because on this you can have a complete description for a lot of loading time. Why we need this? Because if you go for the left side here, so this is like a log 10 scale. So that means here you have like in 10 power minus 6. So something which is very, very small, which is very close to the instantaneous behavior. So you are loading your material and what happened direct after. So it's very close to instantaneous behavior. So this value here, which is very low, and after if you have something which is smaller and smaller, there is like there is no evolution. So this value here is called like instantaneous modulus. So it's also called like E0. It's right in E0. We will see this value after. So some which represents like the instantaneous behavior of the material. So this, if you try to do this on without plotting this master curve, so there is no device which are able to record like with this time base. This is too small, so the device are not enough accurate to do this. And another way, if you go here for the very long time here, so again, if you make this longer and longer, so there is also like a saturation here. And this is a very long-term behavior. So if you remember, this long-term behavior is this epsilon, is this E infinity. So that means the long-term modulus here. Again, if you want to do this, so you can do this without plotting a master curve, but you have to wait many years to get the response. So you don't want to set up an experiment and waiting many years until to be able to get the answer. This is not suitable, so that's why this time temperature superposition principle is very useful for doing this. So by performing experiments only on this time range here, and by using this time temperature superposition principle, so we are able to characterize the behavior as a very close to the instantaneous at a very long term. So this was the purpose of plotting a master curve. So if you fit this master curve with so if you use this model, so here you can deduce the E infinity, and if you take the sum of E epsilon plus all the EI, E infinity plus all the EI, so you get also something that we call E0, so the instantaneous modulus. You will see also this on the exercise. You can also characterize this point. And if you fit with this model, so you can also deduce all the EI. So this is a way of characterizing this the term that you put in the Prony theory. So usually we fix this term. So we'll because this tau I characteristic time, they are used to model the behavior at different characteristic time. So that means you can have we can have a good like a wide interval. So you can take like every power 10 second, for instance, if you work in the log scale. So you can characterize the behavior here. So the number of tau I you decide by yourself, and you fix this value. And the idea is to characterize this term and this term. So this was according relaxation test. Now I want to present you other kind of possibility of characterizing the viscoelastic behavior. by using like a dynamic shear rheometer. So it's an example that you can do this. We can do this kind of test on bitumen. Because bitumen is kind of liquid depending on the temperature, so you cannot perform like a relaxation test on bitumen. It is not practically, it's very difficult to do. So for this, we are doing other kind of test. We are applying sinusoidal shear stress in the structure. So what means the input of the test is stress. So it's not like the relaxation is not the strain, it's the stress. So you apply certain stress, so a shear stress, which is a sinusoidal signal. So since you apply stress as the input, so you want to measure the strain as the output. So on this, if you apply a stress here, you get like a peak stress in your sinusoidal signal, so the maximum stress for one time, and there is and there is like a time delay when you get the maximum strain. So if you look here, the input sinusoidal signals, the highest point here, is not at the same time that the output maximal strain. So there is a time delay between the maximum point. And this time delay represents an indication of the viscosity of your material. So we can calculate like the dynamic shear modulus, which is the ratio between the maximal stress and strain here. And this dynamic shear modulus is decomposed in two parts. One part which is elastic and one part which is viscous. So that's why it's like viscoelastic material. It's a combination of elasticity and viscosity. So this, as I told you, this time delay here represents the angle here between the elastic and viscous part. So what means if you have like this time delay which is equal to 0, so that means this will be only on this part, so it is like an elastic material. What means time delay is equal to 0? That means when the peak on the strain appear at the same time with the peak on the stress. So there is no time delay. So this is a case of a material which is purely elastic. There is no time delay between the input and the output. And on the other way, there is an entire phase of delay. So when this when this phase angle is equal to 90 degrees, so that means here you are only liquid. So it's the same, only viscous is the same is the case of the liquid material. So there is no elasticity, is only viscous material. So if your time delay is higher, so that means you have a material which is which behave more as a liquid. So a viscoelastic material is a material which is something in between this viscous part and elastic part. So this is this DSR. So you can characterize the viscoelasticity of material by using this. How you can plot? So here is not the relaxation modulus, but it's like the shear modulus. And here I plot not in terms of time, but in terms of frequency. But it's the same because you know that time and frequency they are just linked. They are just is the same is an indication of time. So since it's in terms of frequency and not in time, so it's going up. So you can obtain this kind of curve. So again, this is a master curve which has been plotted for bitumen. So it was the same that I explained you before with relaxation test. So here we perform a lot of shear tests for many different temperatures for the same frequency range. So we have a lot of different experiment results, and we can plot a certain master curve here. So this master curve has been plotted for 60 degrees, I guess. And there is like some formula written in the frequency domain. And so on this, you can characterize your G, I, and tau I. So you can use this Prony series. So this Prony series now is the same that this the Prony series written in terms of relaxation modulus, but now is written in terms of shear modulus. But as you already know, like in viscosity, so the Young modulus, shear modulus, bulk modulus, and Poisson ratios are all linked together. So if you find the different value of G infinity and Gi for different tau I, you can, if you know the Poisson ratio of the structures, you can also identify the Young modulus. So you can choose which experiment is appropriate depending of your material in order to identify the viscoelastic parameter. There is also other experiment which is called a dynamic mechanical analysis. Is exactly the same as this DSR. So it's like a sinusoidal input signal, but is not in shear, so is like in compression. So you can you apply like a uniaxial compression, but with a sinusoidal input, and you are performing exactly the same, and you can plot your master curve according to the same principle. So here, for instance, it's a master curve plot on hot mix asphalt. So we perform like different analysis, so different compression tests at different temperature for the same frequency range. We plot a master curve, and you can again fit this master curve to identify the term of your Prony series. So this has been done on asphalt, and this is the same on mastic. So this Prony series, so here the result of this Prony series has been used to fit this on mastic, and this is the Prony series that you are using in the exercise exercise B. Okay, I think we can take a 15-minute break, and we will continue this lecture after. As usual, I will stay here during the break, so you can ask me if there is any question. Great, so we discussed to how characterize the Prony series material parameter. So here is an example of a Prony series with a 8-term with a depending characteristic time, and this long-term Young modulus. So this is the models that you are using in the exercise B, which have been used to fit the behavior of this master curve of mastic. I presented you firstly like the relaxation test. So when you apply displacement and you maintain this displacement constant during time, and you have a relaxation of stress. But now I want to discuss about the creep test. This is another kind of test. So you apply a stress and you maintain the stress constant during your test. So again, since you apply stress and you maintain the stress constant, so stress is the input of your experiment, so you control the stress. So you want to look the strain as output of the strain. So on a CRIP test, the input is stress and the output is strain. So now this is a CRIP test performed on asphalt concrete. In all the material, this is this kind of all the time dependent material. So you have this kind of behavior. So this kind of result for a CRIP test. So you have a first part with a very strong increase, and after you have a second part when you have an increase which is a lot slower, and after you have again an increase of this strain in function of time. So the first part is called a primary CRIP stage. When you have the first increase, so the strain rate here is very high. Second part, secondary CRIP stage. So you have like the decrease in terms of strain rate. So here the strain increases slowly. And you have the third part, which is called tertiary CRIP stage. So where you have an increase of a strain rate again. So we have looked into the material model, which is called Maxwell model, so which is used with Prony series. So if you look into the mathematics of the Prony series, so what happened now? Let's say your time is something which is very small. So you are on this range. So let's say your t, the time 10 to 0. That means this term 10 exponential of 0 is equal to 1. That means you have the sum of e infinity plus all the I. So this is something really close to like the instantaneous behavior when the t tends to 0. So you are able to model this part. So like the direct instantaneous behavior of the material. What happened now when your time increase? So when your time increase, so this is not 1 anymore. And if you increase the time sufficiently long, so let's say your t tends to infinity. So if you have exponential to something, exponential of minus infinity, it gives 0. So that means all these parts will become 0. So what means at the end you will have like only E infinity. So that means if you wait a sufficiently long time by using this Prony series, you will have the stress which will be linear proportional to the strain, and you will have like the relation between the stress and strain which will be E infinity, and this E infinity is not depending of time. So what means for a time sufficiently long, you will have after a while a flat curve. So here you have a decrease of the time contribution, and after a while, using the Prony series, you will have a flat curve. What means this? That means by using a viscoelastic model, by using the Prony series, you will never be able to model the tertiary CRIP stage. This is due to the mathematical formulation of the model. You will never be able to do this. How you can model this tertiary CRIP stage, and why is this tertiary CRIP stage is due to the damage inside the structure. So the third part here of a CRIP test is due to the damage. So now I want to discuss a little bit of damage. I will present you the concept of damage mechanics. Just a parenthesis here. is also I want again to you to be aware of which kind of material model are you using and for which purpose. As we can see here, if you use a viscoelastic model to model the time dependency on a viscoelastic material, this is totally fine. This is very good. But if you try to model the damage, or if you try to model the tertiary creep stage of such kind of material without a damage model, so you can load your material until time extremely long, and you will never see the damage model. You never see the damage occur. Why? Because you don't use damage model. So you always, so it's sometimes it's good to make some simplifications. That means sometimes it's good to don't use damage if you don't want to see this tertiary creep stage, because when you start seeing this, that means your structure have been damaged, and this is increase very fast. So hopefully you don't want to reach this state in your structure. But if you try to model this without using an appropriate damage model, you will never see this. So you have to be aware of the consequences of using this kind of material model. Again, this is very important. So let's discuss a little bit about continuum damage mechanics. As we have seen in the previous lecture, this is a characteristic curve of an elastoplastic material. So characteristic curve is a stress in a function of strain. So we have seen that there is like an elastic part. It can be viscoelastic, or on this, to simplify, is like elastic. And after a while, so you reach the yield stress, initial yield stress, and after you have like an evolution of the yield stress, so you have hardening here. On this case, nonlinear hardening. But you have like the plasticity which occur. What happened in real life? So here there is like a saturation, and you can continue displacement, and you don't have an increase of stress. So there is like saturation. But what happened in real life? After a while, you cannot continue to load your material. You will have like damage. You will have a fracture of your material. So here I plot like the real curve here. So here it's like the real sigma, and I plot with a dashed line behavior here. So this dashed line, so this is like a sigma tilde, is behavior without damage. So we call it like effective stress. So it is a stress in the structure if you don't have any damage. So this is called effective stress. It is called like nominal stress. So this is the real behavior of the structure, and this is what would be the behavior without damage. So now I want to present you like a damage variable, which is calculated, or which is defined by using this ratio, a ratio between the nominal stress and the effective stress. So this is a very easy variable, but which can model the damage evolution. So when you have a D which is equal to 0, that means you have no damage in the structure. So that means there is no difference between your nominal stress and effective stress. And when your D is equal to 1, so that means you have totally damaged the structure. So there is no more material. I will present you why. So this, this D variable is an indication of the integrity of your structure. If D is equal to 0, no damage. And if D is equal to 1, your material is totally broken. So let's go a little bit deeper in the definition of this damage variable. So this is like a piece of material, and inside the piece of material, so you take like a small amount of material. So this is like a RVE, like representative volume element. So it's like a small part of material, but sufficiently large to have a representative, to be representative of the integrity of the material. So if you look this RVE, so this small part of material, so there is like one resisting area, or one cross section here, delta S, and there is like a damaged area here. So this on this surface there is some micro cracks or or voids or whatever, but like which represents which are due to the damage in the structure. So there is also an area due to of this micro void or micro cracks. So this D is a ratio between the damaged area and the resisting area. So that's why when D is equal to 1, so that means the damaged area is equal to the resisting area, to the cross section. So that means you have no more material. You have no more material. That means your cross section is entirely damaged. So there is no resisting stress in this area. So this D is equal to 1. And if D is equal to 0, that means there is no damaged area. So there is no void or no crack in your structure. So your structure is not damaged. So this is the quick idea of the continuum mechanics, continuum damage mechanics. So now, what happens if you load and unload your specimen when you have the damage? So if I plot like the nominal stress in function of the strain, so the real stress and the effective at the same time, if I load my material and I have this plasticity and I have damage, what happened now? When I unload my material without damage, I unload with the same slope as the initial slope, so Young modulus. But when your damage process, when the damage process starts, since you have now a resisting cross section which is smaller, so you have also a decrease of stiffness. So as you can see now, when you unload your material, you can see also this stiffness which is decreasing. So this is a characteristic loading unloading curve for damaged material. So in order to introduce the damage into a elastoplastic model or viscoelastic model or whatever, so what you use, you scale your stiffness by this damage variable 1 minus D. So this was the relation between the stress and the strain in the case of elastoplasticity. If you remember, so if your D is equal to 0, that means you have this classical elastoplastic relation between the stress and strain. And if your D varies, so that means if D is not equal to 0, but if you have an increase of this D, so now you can see that the stiffness will decrease. So the resisting stiffness, all this part, will decrease. So of course, if the resisting stiffness decrease, so to obtain the same amount of stress, so you will need like a higher strain in the structure. So this is the basic idea of the continuum damage mechanics. I will not go through too deep in detail onto this because continuum damage mechanics is quite a complex topic, but this is a very basic overview. It's good for you to know how you can model damage. Yes, Yes, just to close this. So as you can imagine, to compute your tangent stiffness matrix, so you now have to introduce this D variable in the tangent stiffness matrix in order to be able to solve your global systems, your finite element resolution. So even if you have an elastic material with damage, is also a nonlinear material because your damage will vary, so you will not have the same stiffness during all the deformation. So damage damage is also a matter of nonlinearity. So this is an example of a very complex material model, material behavior. So this is a case of combination of everything that we discuss today. For instance, it's like a real behavior of asphalt concrete. It's like a viscoelastic. So you can see the influence of strain rate on the first part, on the viscoelastic part. Viscoplastic. So you can see you have different yield stress depending on the strain rate, and after there is also like damage evolution. So this kind of a real behavior. And of course, so this is like 20 degree, and there is also like a temperature dependency on this. So if you make the same test at 10 degrees, so you will obtain different solution. Unfortunately, this is a case of many material, like asphalt material or polymer material. So they are quite complex to model. So they are quite challenging in terms of material characterization and material modeling. This is the evolution of the damage. So I present you this damage variable between 0 and 1. So here it's like this damage variable D plotted in function of the strain. So you can see that you have like an increase of this damage variable in function of strain, and of course this damage is also depending of the strain rate. So you can see that at the restart D is equal to 0, so that there is no damage in the structure, and at the end is like something that 0.8, and I mean in real life you will not your structure will break down before 1, because 1, that means there is absolutely nothing. So if you have like a resisting area which is sufficiently small, so you will have like breakdown before 1. So here, this case, maybe the curves they can continue a little bit, but when you have like 0.8 damage, 0.8, that means you have 80% of your structure which is air void, or which is no material. So that means your structure is really close to collapse. Yes, so here I want just quickly to present you like how we can model this this complex behavior. So the viscoelasticity, viscoplasticity, and damage. So this is a viscoelastic model coupled with damage that we develop here at KTH. So we have used, as I present you, the we have used viscoelasticity for representing the first part of the curve. So here we have used a 7 term for the Prony series. We have also, so if you look here in the tau I here, you can see that there is like a temperature dependency. So this tau I here, depending on the tau I T0, that means the tau at reference temperature. And after this tau, they are scaled by using temperature dependency. So this is a very easy model to simulate the influence of temperature on the viscoelastic behavior. So that means we characterize the Prunus area for one master curve at one certain temperature that we call reference temperature T0. And by using this formulation, so we are able to characterize the behavior at all the temperature. This is for the viscoplasticity. So if you remember the Perzina model that we discussed, and that one student found that there was a mistake at the denominator. Of course, it was a plus, another minus. So this is like an extension of the Perzina model. So at the numerator, so you can see like a Drucker-Parker tip surface, because you can see that there is like this parameter alpha, which depends on the hydrostatic pressure. Here, trace of sigma, it is the hydrostatic pressure. And the denominator, it was like the the hardening law. Here I just substitute with this nonlinear hardening evolution, as I already present you. And we can also see that this, so the viscosity coefficient here is also depending on the temperature. And there is this damage law. So this is like, if you look here, is like d dot. This represents the evolution of the damage. So I don't want to explain you anything here. I think is out of the scope of this lecture. I just want you to precise that this, of course, is a temperature dependent with the same kind of dependency here. And it's also depending of the stress level. And it's also depending of if you are in a tensile or compression loading. I don't want to go too much in detail, but it's quite a very advanced material model. So in this case, if you try to model the viscoelastic, viscoplastic behavior combined with damage into a vacuum, there is no material in a vacuum which is able to do this. So we have to create our own material model. So here is different results in terms of like different comparison between our model and some experiments. So we can see that we are able to capture like these are creep recovery tests. So we load the test and after we unload the test. So it's kind of advanced test, which is good to characterize the loading and unloading process, cyclic loading. So we can see we are able to have good results in compression, also in tension, because we have to check both, because we have seen that there is a behavior which is totally different in tension and compression. So we have also to be sure that we are able to simulate in both stress state. And of course, at different temperature. So as you can imagine, there is many to do if we want to develop a new material model, and also in terms of modeling itself, and also in terms of characterization of the model. So design appropriate experiment to be able to give into the material which is developed, and to be able to make good finite element simulation. Because again, if you use a very complex material model without a clear idea of which experiment you need to use in order to deduce good material parameter to use in your material model to making your simulation, this is not correct if you don't have a good overview of the complete process. Okay, I just want to finish this lecture by present you like the cohesive ozone models that you will use in the exercise. So I discussed about damage, but it was like a continuum damage mechanics. So that means it was like a damage taken into account at the macro scale. So when all the all the different phases of the material, they are like in one material, the continuum scale. But there is, if you are working like in micro scale, so when you have different different phases in your material, as you have in the exercise, because in the exercise you have like mastic, each one phase aggregates its one other phase. So you have like an interface between the different phases. Some of you maybe already start like the second part of the exercise. So you start to model like an interface like this. So this is an interface in the exercise between the aggregate and the mastic. And this interface can degrade with time and with load. So what means the degradation of the interface? That means that you have decohesion between the aggregate and the mastic. So to be able to model this decohesion or this degradation of interface, so we will use a cohesive zone model. So this is the representation of the cohesive zone model for the mod 1 fracture. If you remember the first lecture that we had together, so the mod 1 lecture, the mod 1 fracture is the opening of the opening mode, so under tension. So basically, it's a criterion which have like one stress, which is a limit. So below this stress, you don't have any damage, so you don't have any degradation of the interface. And once you reach this stress, your damage start in the interface. So your interface start to degrade. So you will simulate the decohesion between the aggregate and the mastic. So in Arrhenius, so this is a cohesive zone model. So here it was like an overview of the mod 1 fracture, but of course you can also have like a shear mode in fracture, so mod 2 and 3. So the damage initiation is not only one value as here in mod 1, but it's a combination of both. So here, if you remember here, it was like the stress in here there are the 3 direction of the stress. This is like tensions on mod 1 and the second and third mode. So you can combine the different shear, in plane shear and out plane shear. So this is like one criterion with a ratio between a different limit. So it can be this one. So here it's like if one ratio is equal to 1, the damage start. In this quadratic criterion is like a combination. So if the combination of the ratio is equal to 1, so the damage start. So this is for the yield. So this is when the damage will start. And once the damage, once the interface start to degrade, there is also like a damage evolution. And this damage evolution can be linear or can be like exponential. There is different aspect. So if you use the quadratic stress, so if you use the combination of different ratio to get the yield, and if you use a linear evolution, so this is what you are using in the exercise B. So this that's it for the cohesive zone model. This also end this lecture. So I want to summarize very quickly what to remember from all the lecture that we had together. So during the first lecture, I discussed a lot about modeling strategy to perform a finite element analysis. So I discussed also some specific aspects for pavement material, but not only. So this is you have to remember the different aspects that we went through. We also we have also seen how to perform a crack analysis. So this is something that you have to remember, because you can use this method on a many semi-engineering structure, not only asphalt. So this is a very good tool that you can use. We went through how we can solve a finite element problem with nonlinear material. So we went through like the Newton raphson, and what is the consequence of using a nonlinear material for the finite element solver. So you must remember this point. After we went through the theory of elastoplasticity, viscoelasticity, and quickly in the viscoplasticity. So this is something that you should know now. And we discussed also a little bit about continuum damage mechanics. So maybe not too deep in terms of theory, but you should understand the concept of continuum damage mechanics. Okay, so this is the end of the lecture. So it's yes, I will as usual. I will stay connected until 12 o'clock, so you can ask me some question about the lecture. And as usual, this afternoon we have 3. I will be connected, and there will be also 2 assistants who can help you for the exercise B. Thank you, and see you this afternoon.